I'm going to be talking to you guys today about how to test your amazing Go code. Let's get started. So testing, is that a thing? I know some people don't write tests, some people do write tests, but testing, what is it all about? It's just to ensure that the code that you write is reliable and is of good quality, and also to prove to yourself and to your colleagues that what you've written is something that works and it is working as you expect it to work. And the nice thing about Go, which a lot of other languages potentially don't have, is that they have some amazing testing packages built in, ready for you to make use of. How do you do that in Go? So let's assume, for argument's sake, that you wrote some code in a package called basic math. And in that package, you have a function called add, and it takes in two integers, so int64s, and it returns an int64 as well. And you want to write a little test for this. Well, in Go, you would be able to, in a separate file, let's call that file math_test.go, be able to write a function called test add, and this function will take in what's called a testing t, and would be able to invoke the function. In this case, we're invoking it with arbitrarily chosen inputs, 1 and 2, and we can then assert or check that when providing this 1 and this 2, that you'd get something that is 3. And if you don't get the 3, that you rather call t.error. And what this will do is, if for some circumstance you go and update this function such that it doesn't do what it's supposed to do, that this error would then be called, and when you run Go test, you would see that this line of code would be displayed on the terminal, saying expected that add 1 and 2 equals 3, and therefore you didn't meet that expectation, right? Cool. So that's all cool, but that one downfall of what we just done there was we wrote our test. If you go back, you'll notice that the test itself is in the same package as the code. So although they're on two separate files, they still sit in the same package, meaning that this test itself actually has access to multiple things inside of this package that it might primarily not want to have access to, like the private members of this package. So if you remember in Go, public things are always capitalized, it starts off with a capital, and private things are, starting off with lowercase letters. So in this case, this is a public member, and we are accessing it as though, like as per normal. But we could have instead rather accessed it like we would as a user of this package. So the suggestion then from Go is to rather move your tests into a _test package. So your code, or they're in the same file, lives in that math.go file, and your test living in that math_test.go file. You could actually change the package of your test to be in a different package than that of your actual code, with the exception that that package has to be the same prefix name of the actual package and has a suffix of _test. So in this case, we can make a slight modification. So instead of just calling the add function directly like we used to, we need to call it through the use of its package. So we need to first import that basic math package, and then invoke the add function that is part of that package, because it's a public member of this package, and pass in the parameters that we want. And then again, do the same thing, assert that given these two parameters, that this is what we expect. And if anything else, it's an error. So this is great, right? So it allows us to separate our actual code and our testing code to be in two separate packages. They already are in two separate files. So it means that I'm not mixing up my testing code and my real code that I want others to make use of. And so no one else can see that testing code if they are a user of my package, which is quite cool. The other benefits of it is that when I'm testing this, I'm testing it as a user of this package. So as a user of this package, how am I interacting with this API? I have no access to the internal workings of this API, and as a result, I'm actually not accidentally manipulating some internals to make sure that this thing works as expected. I'm just using the API that I'm exposing to others and making sure that when I do use the API like others use, that the inputs that I give and the expectations that I get is exactly what I want it to be. Cool. So now we've got that, right? But let's say we wanted to do exactly what we wanted to do previously, where we want to actually make sure that the internals of our code is actually working as expected. So let's go and update our code a little bit. This is some convoluted code, but let's assume that we had a private member called sum, and it kept the last summed value that you just summed inside of its internal state, right? And you return whatever value you get from that's stored there. Then you could write a test that you could want to write a test that firstly tests that this thing works as expected, but also that makes sure that whenever this thing is returning a particular value, that this internal private member of this package also updates accordingly. And the way we would do that in Go is we would separate those kind of tests that tests internal mechanisms of our code in a separate test file. And that test file we would have a suffix of _internal_test.go. So if we started off with a package called basic math, and in there was a math.go file, we would have a math_test file, which would house something like this. And we would introduce a math_internal_test.go file, which would be testing something that tests this private member of this package. And how would that look like? So again, in our test_internal_test.go file, we would have, for example, in this case, a test add function again. And the only thing that's different, if you can recall, is we're not referencing the package here anymore. We're just calling add because now we are part of the package. So we don't need to self-reference ourselves. And what we can then do is we can actually directly access the internal variable called sum, the one that was defined over there. We can access that over here and assert that that internal variable is what we expect it to be. So in this case, calling add and passing 1 and 2, we expect that the output should be 3. And if not, we are calling t.error. We are then also asserting or checking if that the internal property sum also has that same value. And if not, then call t.error. Okay, so note again that this allows us to do a little bit of more extra testing, calling our functions that we want to call to test whatever we want to test, but also double checking our state, our internal state, so that we are making sure that it's working as we think it should work. We can think of these tests as being a little bit more brittle because it's not what an actual user of our package would do or would care about. No user is caring about this internal sum property. They're only caring about the outcome of this API that we've exposed. So if you're thinking of it, this is just testing that brittleness of our code to make sure that it's working internally as consistently as it possibly can. Okay. But now, that's all great, but if you look at all our cases, right, like there wasn't a lot of variety. So if you look at it, we just tested one case the whole time, that 1 + 2 is 3. What if we had a bug where when adding 2 and 2, or when adding -1 and +1, it actually returns something that we didn't anticipate, right? We would actually need to add a bit more variety to our test here to make sure that not only are we testing our function, but we actually have sufficient coverage for sufficient use cases of our code. So Go has a nice way of handling this through what's called table-driven tests, right? And if you were to think of it, instead of just having one function call and hard-coded parameters going into it, you can actually create an array of of data inputs and data outputs, and make sure that given those inputs, you assert that they are the exact outputs that you want. And the nice benefit of this is you can create this long list of different cases and use those cases to assert that your code works. So let's say, for argument's sake, you pick up a bug in production that this add function now doesn't work anymore in a particular manner, what you should do after fixing it is prove that you've actually fixed it by adding a new case. And so this essentially becomes this long list of proven records of, potential edge cases or cases that you should cover, potential cases of resolved bugs that you have collected over the years to make sure that your code is more resilient as you go with time. And it makes, eventually, if you have this long list, it makes it quite easy to maintain and easy to recognize that something is off and how the function should behave and how it's also some sort of form of documentation if you think about it, right? So you can be able to see, oh, okay, cool. If given these inputs, I'm expecting that output. And given these other inputs, there's a completely different output that I'm expecting, which is quite cool. So how does that all look like? So to update our initial test, it's quite a bit of changes. But if you just go revisit our initial test over there, the initial test was just a function, and it has one if statement, and all it's doing is calling the thing that we want to test, giving hard-coded inputs and expecting a hard-coded output. And then if it's not expecting that, it's calling t.error. So with table-driven tests, things are slightly different. So you can still see in the nutshell, if I was to highlight this, you can still see that there's some makeup of what we were doing in the past, right? There was an if statement where we called our function on some package, giving it some inputs. But this time it seems like it's arbitrary inputs. And then also then asserting that if it's not the same, we should call t.error. But what's going on here? So if you look at it, the first main ingredient is this thing over here, which is an anonymous struct or an array of anonymous structs. And these structs are made up of these fields. In this case, a field has a name. These are A and B. We're just calling them the inputs. And then want is what we desire to have at the end, right? And you can set this up and you can add some cases over here. And these cases would look like this, where you define these structs, the values in these structs. So you can set the name for the one, a case when -1 + 1 is equal to 0, and you can set A to be -1 and B to be 1, and then we want that the output of it to be 0. So you can fill that in here where there's to do is over here. And you'll notice that now what we're going to be doing instead is we're going to be looping over these test cases. So essentially this thing here is an array of cases, and we can loop over them. And for each case, we want to call a thing called t.run. It's part of a function that's part of the testing t package or testing t type. It has a function called run, and it will run each case for you as independent test cases. So if one fails, it will report an error saying your second case failed, and this is the reason why it failed, which is quite cool. Yeah. So with this said, when you use sort of table-driven tests, it's a little bit of a better upgrade. It allows you to write more cases, allows you to write more. Your code is a bit more easier to read and reason about. And if ever you need to add or handle extra cases, it's very easy just to add a new case or mutate an existing case, because you can just go and add one of these or update one of them, which is quite cool. Okay, but now what can we do with all these ifs? So if you look at it, you have all of these ifs in your code. It looks a bit hard to read a little bit, right? Can't we improve it a little bit? Well, yeah, that's quite cool. We can. There's a package in the Go community called Stretcher Testify, and it has a sub package called assert that you could potentially use. So, and it uses the assertion paradigm, where instead you get a value and you just assert that this value and this what you expect is matches or is the same. And there's some nice APIs on this assert package, such as the equal API. And in this case, we could resolve writing this if statement over here, where you're asserting that something is not the value of something else, and then erroring in that condition. You can convert that into this assert.equal pattern. And you can say, okay, assert.equal, that what we want must be equal to what we got. And if not, then it automatically errors for you. So we don't need to handle the error statements. We don't need to make sure that we write some pretty error message over here for us later to consider and know which thing failed and which thing was the problem. It handles all of that for you. So that just changes this code up slightly and makes it a bit more easier to read and easier again to reason about. So this is a nice package in the Go community, and I think especially at Luna, we make use of it as well. So it's a good idea to also consider using it. But now, what about this case? What if we had a function, let's call it list all, right? And it returned a slice of gopher words. And this is, again, some arbitrary thing that I wrote. But let's assume that this was a big, large payload. In this case, it's not maybe that large, but just imagine this was times 10 or times 1,000. Sometimes when you have an API and like a RESTful API and it returns some payload, there might be a lot of stuff that is returning, and you actually want to assert that that payload that you got is actually what you want to get and is what you expected. Then there's another package that we can make use of, and that's another package in the Go community by Seb Da called Goldie. And it's nice because it allows you to get a large bundle or large payload, store such a payload in a file, and then read the file and assert that what's the contents that's in the file and the content that you got back from the API or this function call matches. So you don't need to then maintain it in your array over here, because you can imagine if I was to say that there was one test case like this, and the thing that we wanted was this large output, you can imagine if we have multiple test cases that our Go file will like grow quite drastically because we have all of these large outputs that we are putting in this want. So what we could do is we could defer that to a file and store it in a file and use Goldie to read the file, the contents in the file, and match that it matches the expected output that we got from this function. And how does that look like? Well, again, you can the line that we had here where we had assert.equal, we can actually change it up. We can say goldie.assert JSON. And this example, for example, asserts that the output that you got when you JSON marshal it, it matches the output that you have stored in this file, right? Which is quite cool. So you'll notice that here we don't actually have a tt.want. We actually, the want that we want is stored in some file named a certain thing, and we are then asserting that the thing that's stored in this file matches the expected data that we got back from this list all function. So what's happening here? Well, Goldie, as I said, will read pre-generated golden files and then compare the output that the function has with that pre-generated golden file. We don't have a need for a tt.want, and these golden files can be generated on whenever you run go test /update. So whenever you run your test and you pass in this update command, it will automatically go and refresh your golden files and update your golden files. And every other subsequent go test that you run will always just compare the current output that's coming back from your function with what you've already pre-generated in the past. Yeah. So how does all of this look in one go? So like a pro tip, something that we also use quite a bit at Luno is we make use of go generate as well. So we add to our, like just above our test function, we add a go generate command, and we say, okay, cool, go generate, go test, and run the actual test function with the update command. And then what this does is whenever you run go generate on your project or whatever, it will automatically go and execute these tests and update the golden files. And you can see, oh, hey, when I ran all my go generate, my golden files have changed. So there must have been something that has happened with our API or with our function or something that made these golden files change if that was not intended, which is quite cool. And some IDEs as well allows you to gives you like a little run button that you can click and keep them up to date whenever you want to. So it's quite nice to make use of that little pro tip when sorting out your golden files. And that's about it.
Thanks, Chad. That was awesome. I just had one question for you. So one thing that I sometimes find with table-driven tests is that Like if you have lots of test cases and the test cases are quite complex, like they have lots of properties, that if you go right to the top of the list, like the first few cases, they're really, really far away from the actual logic of the test. Like you have to, if you change the test case, you have to scroll like way, way down until you eventually get to that for loop at the bottom. I was just wondering if it's something you've noticed, and if so, do you think there's something we can do about that?
Yeah, so sometimes I get your feeling, right? Like sometimes you got long test cases and it's a lot of scrolling effort. Depending on the tool or IDE that you use, you can squash it, you can do all of that. But I still think that's a little bit of pain to endure for adding as much test cases to your code as possible. I'm not so sure what other alternatives exist to improve that sort of experience. Maybe you could use, like I just suggested, this Goldie approach as well. Maybe you could use Goldie in some sort of sense of the word, to shrink down your test cases. So you could have maybe an input file that defines all the inputs, and an output file that defines the outputs of your test. And so then in your test cases, you are just referencing those input and output files and using that, rather than configuring your test cases to be these large things. Maybe that can help reduce it a little bit. But I suppose it depends on the actual data that you're passing into your functions that you're testing, and seeing what that looks like. But yeah, maybe that's the best thing I can think of, at least. Otherwise,
cool.
You need to suffer through the pain.
Cool, thanks. Got another question from Peter. He says, do you test methods on a type, since it seems methods generally get covered by the code calling it? So do you test methods on a type?
Mm-hmm. So I would say depends on the situation, but I generally love to test as much stuff as I possibly can. Sometimes, so the point I think is sometimes you write some code, maybe there's some other code that gets tested as like by the way while testing some other function, because that function somehow makes use of another function. But there's circumstances where in your code that you are testing, you're not fully covering all the cases of that other function. And the responsibility of your code isn't fully, doesn't fully make use of that other function. So that function might have some extra responsibilities, it might do some extra things, but you're not using all of what it offers, or all of what it does. So it would always be wise, I would think, to write tests for both the code that you are currently trying to test and some other code that you are dependent on that you also own. Because they serve two separate use cases or two separate purposes. So I would imagine those types that have methods or pointer receivers or whatever, you should also write some tests for them as well.
Mm-hmm. Cool. Slightly related to that, from Claudia, what's your opinion on the amount of code that should be covered by one test? Should it be whole flows, one piece of logic, mocking everything that isn't that one piece of logic?
Good question. So I think my opinion, so great that is my opinion, I can share my opinion. So I think my opinion is the more tests, the better. But tests is an expense, right? Writing test code does come with a bit of expense because it needs to be maintained and all of that. You could also mock out everything in your code, but is that really testing it? Maybe to some extent. So I think a good rule of thumb would be to make sure that your coverage that you have is sufficient. So if you have a function that is maybe calling a lot of third parties, maybe you want to worry about the interaction with your function or your API with those third party APIs. And under certain circumstances, you only care about certain circumstances where maybe some failures could happen and you want to know how your code reacts to that. Maybe that function or that API has 10 times more other scenarios, and maybe those are very unlikely to happen. Should you cater for that right now, when you start writing your code, maybe not. Maybe wait. Maybe defer that to when something in production happens, and that's something that now is a thing. So when you go out and fix that thing in production, you can then write a test to prove that the thing that you just did was fixed. So I think there needs to be a balance. It needs to be pragmatic. You obviously can't write infinitely many amounts of tests, but I think just having a good sense of coverage around what are sensible things as you write your code to cater for makes some pragmatic sense, I think.
Awesome. Claudia, I hope that answers your question. We've got a question from Ruan. Any comment on fuzzy testing coming to Go 1.18?
I'm not so sure about that. I've seen in the Go community, in the Go blog, that they are talking about adding that into the standard library, and that's going to be awesome, I suppose. The use of fuzzy things is quite useful. That's probably another thing I can talk about some other time. But it's making sure. So sometimes you're just for everybody's context of what that means is sometimes you have some code and your test cases that you have maybe are very specific to the data that you're providing it. And the nice thing about the fuzzy package or the fuzzy mentality is that those values that you're giving are somewhat random, to prevent that there are certain test cases that you might not have thought about, but some randomness makes things a bit more how can I say? You don't have certain code or certain side effects that you are not aware of, and that randomness, introducing some element of randomness, allows you to sort of handle those side effects that you might not be aware of. And that being in the standard lab, I think that would be nice. And I don't know too much about it yet, but I think it is coming, and it will be nice.
Cool, thanks. Got a question from Clara. Do you also find it difficult to get high code coverage in Go code because of all the explicit error cases? Any tips to cover these besides mocking?
What do you mean particularly with explicit error cases? I would imagine, so in just a simple example, let's say you have a function and it can return different types of errors, and those errors are returned under certain circumstances. Yes, you can, and maybe those things have third-party dependencies, like it's a dependency on some sort of MySQL database, and when you do an insert, only then this particular error is going to happen or something. And then you have an option of either writing a little mock or creating an interface that sort of pretends to be similar, like pretends to be your MySQL instance, and then trying to assert that the errors that you get, like faking those errors and then making sure that the errors that you get is what you expect. That's one approach. And I think that's what most Gophers do. They would use interfaces to help test out certain edge cases or hard to reach parts of the code. But do you really need to worry about that sometimes? Maybe not. Unless that is something that's really, really something that you really want. You really want your coverage to be at 100%. I think that is a little bit hard to reach sometimes. So I think I don't think we should all strive for 100% coverage. I think I think good coverage is the mantra that I think people should have. That the test cases that you're thinking of are well thought through, are edge cases that you think that you should be catering for, and that there's some variety. Whether you cover all your code or not, I don't think it's all that important. Provided I think you should just cover the critical parts of your code. There are some, if error is null, like if any random error can happen, like your database disappears or something. Does that really happen like in real life? Maybe not. So maybe those cases are really hard to get coverage for. So I think that's okay. You don't need to worry too much about that.
Cool, thanks. It looks like, okay, that's the end of the questions. Chad, thanks very much. We can